Greetings, dear friends. After a recent video about repairing a Fujida car dashcam, one of my subscribers contacted me with the same device. It won't turn on. The defect appeared for no apparent reason. We simply unplugged the dashcam from the cigarette lighter, plugged it back in an hour later, and that's it, it's not working. Currently, when connecting the power cable, the current draw exceeds 4A. This is a very high current for such a device. Normally, the current draw should be no more than 1A, hardly more. You can't keep the device running for long with this current, as it could burn out the circuit board. So, I quickly disconnect the cable. There must be a short circuit on the electronics board of this dashcam. My task is to determine the exact problem and fix it. Well, let's get started, and let's start, of course, with the most basic. It's possible that the problem isn't with the dashcam itself, but with its magnetic mount, which I think is quite logical, since it's through this mount that the device receives power. But no, without a power consumption recorder, it's not possible. The problem lies specifically with the recorder itself. It needs to be disassembled and the electronic circuit boards inspected. 4A of current consumption usually leaves traces on the board that can be easily diagnosed even with a simple visual inspection. I unscrew the screws. The threads for them are stripped. Now they simply spin in their mounting holes. This looks like the aftermath of a previous repair. You can even see traces of careless disassembly on the case here. I use the dent to pre-tighten the screws with a spudger and unscrew them. Next, I unclip the fasteners and open the cover. Carefully peel off the metallized tape. I cut it off, as it cannot be reused. I'll need to apply new tape. Next, I peel off the Kapton tape and, finally, disconnect the display cable. I remove the metal screen from the electronic circuit board and inspect it for obvious defects. No obvious problems immediately catch my eye, so I move on to measurements. What should we check? I think we should start by checking the input power supply. The relevant contacts are marked next to the magnetic mounting block. We're interested in the PVR and GND contacts. There's no low resistance here. At 4A and 5 volts, the resistance should drop to almost 1 ohm somewhere. Clearly, the problem isn't with the input power supply, but with some other circuit. Rather than wasting time looking for a needle in a haystack, it's easier to grab a thermal imager and at least roughly see the problematic area of the board. 4A, in my experience, will be clearly visible in the overall thermal image. I briefly connect the power supply. It gets hot here and there. Well, that's at least something. Apparently, the problematic component that's drawing such a high current is located somewhere around here. However, there's no short circuit in the identified areas of the board, which makes it difficult to find. I remove the board from the case to inspect its condition from the back. Maybe there's something there that can help me identify the problematic component. Upon quick inspection, the only thing that caught my eye was this darkened patch of sealant above the ceramic capacitor. However, when I tested the capacitor, everything was fine. There was no low resistance. That's definitely not the problem. I removed the screen and found no obvious defects underneath. I tested the power supply chokes. Everything is fine. There is no low resistance. I found a short circuit at the contacts of the supercapacitor. It's used here instead of a battery. I unsoldered it. The short circuit remained, but this is obviously normal, since the supercapacitor charges during measurement. And until the voltage across it equals the voltage across the probes, the short circuit will continue to be displayed. Now let's look at the contacts on the board where the supercapacitor is connected. The resistance there is quite low, which is no longer normal. I'm checking the data logger's behavior with the supercapacitor disconnected. The increased consumption remained, which also confirms that the supercapacitor isn't the issue. To make things easier, don't move the board around. I connected the power wires directly to the supercapacitor contacts. Now I can supply power from a laboratory power source with the required current limit. 1A will be enough. Now I simply find the components that are generating the most heat. I desolder them and thus check whether they are the issue or not, and whether the excessive consumption disappears. This method didn't yield any significant results, although I even found a capacitor that was presumably shorted. However, when I desoldered and tested it, it turned out to be working properly. The short circuit remained on the board. On the opposite side of the heating point is a small battery, which even has a small voltage. And who would have thought that the problem could be related to it? I decided to desolder it, and that's when the cause of the defect was discovered. The battery had leaked a little, and liquid had gotten onto the board, causing a short circuit. Despite the mask insulating the board's tracks, if there had been some insulation, even a piece of electrical tape, under the battery, this definitely wouldn't have happened. Well, it's good that the cause of the malfunction has been identified. Next, I need to check for burnout somewhere in the inner layers of the board. To do this, I clean off any traces of oxide and connect the power supply to the board. Excellent, the power consumption has disappeared. Let's examine the contact area between the board and the battery under a microscope. There's a black spot. I check how far it extends into the board. It's safe to say the board is almost undamaged. In this case, it's enough to simply clean off all the blackness and, ideally, apply some insulation. Zap lacquer, for example, would work. However, it's inconvenient that you have to wait for it to dry. A blower won't do much to speed up the curing time. Besides, the lacquer will blow off. Heating with a hairdryer works better, but you need to use the minimum heat setting, that is, no more than 100 degrees, since white spots appear at 150 degrees. Now, regarding the battery, it's leaking. This is clearly not some kind of condensation, judging by the color of the deposits. It's clearly electrolyte. The battery needs replacing. It's the ML621 model. The dimensions are in the picture. They are also available on AliExpress, but I decided to get a donor one to avoid waiting for an order. Judging by its appearance, it's in good condition. I install it in its new location. I insulate the area under the battery with Kapton tape to ensure there are no further problems. Done. I connect the power supply and check the charging system. The battery voltage rises, meaning everything is fine. I can reinstall the desoldered components, reassemble the device, and proceed to testing. The device is assembled. I connect the power cable. Consumption is 900 milliamperes. The recorder starts up. The camera image is available. The speed is displayed, which means it's receiving a GPS signal. In my area, the GPS signal is slightly modified, so the dashcam detects movement. I tested the device. All the basic functions are working. I checked the standard adapter, which runs off the 12-volt cigarette lighter. Everything is fine. Basically, that's all I needed to complete the repair. The dashcam has already been sent back to the owner. I hope it works for a long time. In any case, I think the leaky battery issue won't happen again. Dear friends, that's all I have to say for today. Don't forget that we also have a Telegram channel where I post about the latest repairs, which may not even make it into video format. Join us so you don't miss a thing. Thank you all for your attention, and see you at other repairs. See you soon, Tamsta.